Hi, I'm Rudini Sampaio from Park Research Group in Fortaleza, Brazil. I'll talk about the spy game on graphs, FPT algorithm, and results on graph products. This is a joint work with Renato Costa and Nicolas Martins. In the SD spy game on graphs, where S is always at least 2 is the spy speed, and D at least 0, the surveillance distance, we have a graph G in an integer K. One spy and K guards occupy vertices of G. The spy is placed first, and then the guards are placed. Turn by turn, the spy may move along at most S edges, the spy speed, and then each guard may move along one edge. The spy wins if she reaches a vertex at distance greater than D from each guard. The guards win if a game configuration is played again, is repeated. The guard number G and SD of G is the minimum K such that the guards have a winning strategy. K is the number of guards. Here we have an example with a P4 and an example with a P5. If we have spy speed 2 and surveillance distance 0, we need a guard in the same vertex of the spy. One guard cannot surveil the spy. For example, the spy in the vertex B can go to the vertex D, and this guard G1 cannot surveil the spy. Two guards are sufficient since we can have a guard surveilling the vertices A and B and a guard surveilling the vertices C and D. Two vertices are necessary and sufficient. Okay. In the P5 with surveillance distance 0, the spy can go from the vertex C to the vertex A to the vertex E, and two guards cannot surveil the spy. We need at least 3 guards, and 3 guards are sufficient. One guard can surveil the vertices A and B, one guard surveil the vertices D and E, and one guard surveilling the vertex C. With surveillance distance 1 and spy speed 2, one guard is sufficient. One guard can, in the P4, can surveil the vertices B and C if the spy is in the vertex A and go to the vertex C, for example, or if the distance, the speed was greater than 3, for example, goes to the vertex D, the guard can go to the vertex C, surveilling the spy. In the P5, one guard in the vertices B, C, and D can surveil the spy. For example, the spy in A can, the spy in A, the vertex A, the guard in vertex B is surveilling the spy. The guard can go to C and then can go to E, but the guard can go to C again and go to D, surveilling the spy. One guard is sufficient. Known results. The spy game was introduced in 2016, where exact values were obtained in path and cycles. In 2018, NP hardness results were obtained for any S at least 2 and D at least 0. In 2020, polynomial time algorithms were obtained in trees. There are other known pursuit games on graphs. The Cops and the Robber is the classic one, introduced in 1983 from Novakovsky and Winkler. Cops are placed first and win if a cop occupies the same vertex of the robber. This is a well-studied game with many variants, a lot of papers, and one book from Bonato and Novakovsky. This is similar with spy speed 1, if the guards were placed first in the spy game. But with spy speed at least 2, the spy game and the cops and the robber game are very different games. In the eternal domination game is the same as in the spy game with surveillance distance equal to the diameter of the graph. Our results. We begin the study of the spy game in grids and graph products. We obtain an upper bound on the strong product. The guard number of the strong product is at most the product of the guard numbers. We obtain examples with king grids that match this upper bound and others for which the guard number is smaller. We prove that this upper bound fails in the Cartesian and the lexicographical products. In the lexicographical products, we obtain the sective value for any distance d at least 2. We also obtain an XP algorithm parameterized by the number k of guards for any speed and any distance. We obtain an FPT algorithm from this XP algorithm parameterized by the P4 fullness of the graph, solving a game on graphs for many graph classes. And we also extend the NP hardness results of Cohen et al. In 2018 to bipartite graphs. This is a very technical result. Let us begin with the strong product on the SPY game on graphs. The strong product of G1 and G2 has vertex set VG1, Cartesian product VG2, and vertices U1, U2, and V1, V2 are adjacent if and only if U1 is equal to V1 and U2, V2 is an edge of G2, or E2 is equal to V2 and U1, V1 is an edge of G1, or U1, V1 is an edge of G1 and U2, V2 is an edge of G2. The king grid NM is the strong product of two path graphs Pn by Pm. Here, the king grid for 3 is the strong product of P4 and P3. P4 here, P3 here. Okay? So, if S is at least 2 and D is at least 0, the guard number of the strong product of G1 and G2 is at most the product of the guard numbers of G1 and G2. Moreover, the equality holds if G and SD, the guard number of G1 is 1 or the guard number of G2 is 1. This is an if, not if and only if, just if. A proof sketch, we combine winning strategies in G1 and G2. For any guard H1 in a vertex V1 of G1, and any guard H2 in a vertex V2 of G2, consider a graph H1, H2 in the vertex V1, V2 of the strong product of G1 and G2. Okay? This is the main idea of the proof. We obtain the equality when the guard numbers of G1 and G2 is 2. For example, if we have D at least 0, S at least D plus 2, the guard number of P2D plus 4 is equal to 2, and the guard number of the strong product of 2P2D plus 4 is equal to 4. Here we have an example with D equal to 0. We have a P4 here and a P4 here. This king grid for 4. We can divide this grid in 4 parts, and we need a guard always in each one of these parts. This is because we need 4 guards. For example, we have the SPY here in this vertex. We have 3 guards. For example, guard 1, guard 2, and guard 3 with surveillance distance 0. The SPY can go to this vertex and no guard can surveil the SPY in one time step. Okay? With distance D equal to 1, we have the same thing here. For example, we have 4 parts of this king grid. We need 1 guard in each one of them. For example, if the SPY is here, she can go to this vertex and no guard can surveil the SPY. We need 4 guards. Okay, and one example with when the guard number of the strong product is smaller than the product, is smaller than 4 in this example. The guard numbers are 2 and the guard number of the strong product is smaller than 4. Here one example, if the SPY is in this vertex with distance D, 1 guard must be in the same vertex of the SPY and other guards is in the center of the skinny grid. If the spy goes to S, the guard in the center will surveil the spy, and the guard surveilling the spy goes to the center. The guards are changing roles at any turn. Okay, if the spy goes to 1, the guard in surveilling the spy goes to the center, and the guard in the center will surveil the spy. The same here. If the guard goes to the extreme point, the guard surveilling the spy goes to the center. The guard in the center will surveil the spy. Okay, we also show that the guard number of the strong product can be close to the product of the guard numbers. For example, if we have this example where we need k plus 1 guards, and the guard number of the strong product is at most k plus 1 square. Of course, this is the upper bound, and at least k square. In the Cartesian products, we prove that that upper bound fails. For example, here the easy one, it's easy to see that the spy can go to an extreme point, and then one guard cannot survey the spy. Recall that in the P5, Gn to 1, S equal to 2, D equal to 1 is only one guard is sufficient. 1 square is 1, but we need at least 4 vertices here in the Cartesian product. In the lexicographical product, we also need at least 2 vertices, since, for example, if the spy is here, this guard is surveilling the spy. If the guard can go to S, to this point, the guard cannot go in the same line to surveying the spy. So the guard must go to a vertex of this line or this line, for example, here, and then the spy goes to this extreme point, and the guard cannot surveil the spy. However, in the lexicographical product, we can show that if the surveillance distance is at least 2, we have a better upper bound. In fact, we have an equality. If G1 has no isolated vertex, the guard number of G1 and G2 is the guard number of G1. Otherwise, it is the maximum among the guard number of G1 and the guard number of G2. We also obtain an XP algorithm on the number of guards. It is possible to decide in XP time O n to 3k plus 2 if the spy has a winning strategy against k guards in the SD spy game on G, for n as at least 2 and D at least 0. Here we have a sketch of the proof. We have 2 times n to k plus 1 game configurations, since we have 1 spy and k guards, and we have a configuration in which the spy is the next to move, which we call spy configuration, and a configuration in which the guards are the next to move, which we call a guard configuration. We say that a spy configuration is a spy winning configuration if the spy is at distance greater than D from any guard. We initially mark all spy winning configurations, and we repeat the following until no more configurations are marked. Mark the guard configurations that only lead to marked spy configurations. That is, any guard's move will lead to a spy winning configuration. Then we mark the spy configurations that lead to at least one marked guard configuration. That is, there is a spy's move which leads to a spy winning configuration. With this, if there is a vertex U such that any spy configuration with the spy in this vertex U is marked, then the SPY has a winning strategy by occupying this vertex U first. Otherwise, the guards have a winning strategy. This is the main idea of the proof. With this XP algorithm, we obtain an FPT algorithm on the P4 fewness of the graph. And we also solve the SPY game decision problem for many graph classes. G is a QQ-4 graph for Q at least 4 if any subset of at most Q vertices induces Q-4 distinct P4s. Co-graphs are the 4-0 graphs and P4 sparse are the 5-1 graphs. The P4 fewness Q of G is the minimum Q such that G is a QQ-4 graph. They are called graph with few P4s and are on the top of a very known hierarchy of graph classes. They also have a nice recursive decomposition based on operations such as unions, joins, spiders, and small separable components. Here we have this hierarchy of graph classes, QQ-4 graphs here, P4 tidy graphs here. The blue graph classes are the graph classes which we solve the decision problem of the SPY game. The extended P4-Laden and P4-Laden graphs include split graphs, and so they are NP-complete. The SPY game is NP-complete with distance 0, but with distance 1, we can solve it also for these graph classes. Distance at least 1, we solve the SPY game decision problem for all this hierarchy of graph classes. Okay, in the union of two graphs, we have no edge between G1 and G2. In the join, we have all edges between G1 and G2. And this spider, a graph G is a spider if it has a partition RCS with this structure. We have thin spiders and thick spiders. Our first lemma, the guard number of the union of two graphs is the maximum among the guard numbers. The guard number of the join of two graphs is 1 or 2. 1 if the distance, surveillance distance is at least 1, or G1 and G2 are complete, and 2 otherwise. If a graph G is a spider, we have that the guard number is 1 if the surveillance distance is at least 1. If the surveillance distance is 0, it depends if it is a thin spider or a thick spider. It is C, the number, the size of the click, if R is empty, or C+1 otherwise. If in thin spiders, in thick spiders, it is 2 if R is empty, and 3 otherwise. Okay. We also prove a lemma for p-connected components. Let G be a separable p-component H of the graph G with size smaller than Q, with a bipartition H1 and H2 such that any vertex of G minus H is adjacent to every vertex of H1 and non-adjacent to every vertex of H2. Then the guard number of G is the guard number of the reduced graph of G, which is at most Q, where GR is the reduced graph obtained from G by replacing G minus H by 2 adjacent or 2 non-adjacent vertices, depending whether G minus H is complete or not. Since H has at most Q vertices, GR has at most Q+1 vertices. Then, using the decomposition theorems in terms of unions, joins, quasi-spiders, and separable p-components, we can solve the SPY game decision problems in QQ-4 graphs and P4 tidy graphs, computing GN, the guard number of G. Using that XP algorithm for fixed Q, we obtain an FPT algorithm on the P4 fewness of the graph. Solving for all these graph classes and also for these graph classes when D is at least 1. Finally, we extend our hardness result from 2018 to bipartite graphs. This is a very, very technical result. It's a reduction from the set cover problem, which is divided in 6 cases. For example, case 1, when the SPY speed is greater than 2D plus 2, the surveillance distance. Case 2, when it is equal to 2D plus 2. And case 3, when it is greater than D plus 1 and smaller than 2D plus 2. Okay? Just showing some examples we have here, all cases for distance D equal to 0, surveillance distance 0, with SPY speed at least 3 and SPY speed 2. For surveillance distance 1, we have here SPY speed 3, SPY speed at least 5, SPY speed 4, and SPY speed 2. Okay, that's it. Thank you very much.